Okay, so our unit packet and then the packet I gave us yesterday. So your unit packet has a bunch of area. Of course, maybe you've written on the front, but you have the whole back. I'd love for us to just give a quick practice of shorthand electron configuration, and that might be a great place that you place your work. And I thought we'd be a little thematic. So could I ask you, just to kind of warm us up today, to provide the shorthand configuration of rubidium, ruthenium, and radon. So we're going with our R elements. All right, so dig in. This should take maybe 2 or 3 minutes. Remember, easy way to make sure we have not forgotten any of our blocks is to add up the exponents, our electrons that we're adding to our noble gas, and make sure that delivers the number of electrons for your element. Okay. All right, you let me know what clarity is needed. No hesitation. So rubidium being, of course, in the first column. So we know it's the first position of the S block. Well, which S? We want to count down period numbers. 1, 2, 3, 4, 5. So it's 5s1. However, we need all of the electrons leading to the valence. So we go up a period and we begin with krypton in brackets. So for ruthenium, it is in the 5th period. So we go up to the 4th and krypton in brackets. Then to work our way to ruthenium, we first go through the S block, which S, it's the same as the period number, and we need both of them. Then we enter the D block, which D, it's 1 minus the period number. So in the 5th period, it's 4D, 1, 2, 3, 4, 5, 6 over. Then radon. So we start with xenon. Radon is in the 6th period. So we first have to go through the S block. Then we have to remember, and I think this periodic table helps us a little in that this element block's a little weird to remind us, don't forget the F block. So we have to remember after 6s that we go to the F, then back up to the D, and we'll need all of them. And then radon is, 4p is the 6th position over in 6p. So that would be xenon, brackets, 6s2, 4f14, 5d10, 6p6. A way that, again, we could quick check ourselves is if we add and we're 14 less. That's usually a good way to remind ourselves, oh, yike, we have to remember that F block. Questions? I'm not convinced. No issues? We all remembered that, or just needed to be reminded? So we know on Friday that we'll need, maybe to create these ourselves, but definitely, I think a knowledge of shorthand really helps with our understanding of the periodic table and reaction behavior and so on. But these could be involved in multiple choice as well. Questions? Please don't hesitate. We're good? Then, where are we going the rest of our time? I would love for us to pick up with periodic trend of size. Now, if we could then, we're gonna keep going back and forth into this packet, but we are on what is identified as page 10, but it's not, of course, the 10th page in this, the back of this first sheet. And I want to invite you, if you like, to do different colors. And if you'd like a different color, come on board, no problem. So what I'd like to do is to make sure that we've gone through this, which I think is the most important periodic trend to understand. If you invest mentally in this, so this is kind of the mental, hard part. If you really commit the next 5 or 6 minutes to really dig in and get any concern addressed and make sure that you feel confident that you actually could teach it to someone who's absent today, that you could explain not just what the trend is, but why. And then we're going to apply our understanding to these questions, then all the rest of the trends just fall all into place. So we'll take like 5, 6, 7 minutes to develop our way through this page, address any concerns. Then you'll answer these questions. We'll check each other. Then we'll talk about, will the size change when we form an anion or cation? Answer some questions. And then ionization energy, electron affinity, electronegativity, all the while stopping and pausing and answering questions as we go. We talked about the history of the periodic table, the general design as far as terminology, periods, groups, families, where are metals, non-metals, metalloids, what are their general properties? And then the families. And can we compare and contrast them? And we, here's kind of the final chart of the information that you were given yesterday. Then, based upon where an element is, we can actually predict how large it is. And that can help with reactivity as well. So that's where we're going to start to go. All right, concerns. Do we know that there's different periodic tables? There's circular tables. There's tables that elements are ordered just one after another, but for a different property other than atomic number. There are, I'll show us some different ones tomorrow. There's this, it looks like, I think, Starship Enterprise. There's like a table that looks like this. So different scientists have tried different organizations. And if you're researching and applying specifically their method of organization, maybe it makes more sense to you. But truly, this boxy thing is the most used. So this had stood the time and serves us the best. So we want to make sure we understand why. All right. So Nick, on mine, I have these green dots. What are those supposed to be? Yeah. Now, do you mean like volume? Yeah. Okay. I just want us to know how incredibly small the nucleus is. And of course, we can have one proton, gosh, up to 120 or so. But we have to just always know it is so crazy small and crazy dense. As we add protons, yeah, volume increases a little bit. But more, the addition of protons changes what these terms are. So we've gotten period, group, family. Well, now we have the addition of these terms. So this is beneath the table that we started to add to. All of those terms can be used synonymously. So just like max, cool, awesome, tall, very smart, all represent you, sir. These can be used interchangeably. Nuclear charge, nuclear strength, effective nuclear charge, and then we can symbolize that with a Z with a little EFF. And the EFF means effective. The Z, atomic number. So in other words, we could use either of these terms to mean the number of protons in our nucleus. Okay, that's what I'm trying to show with the green spheres. Okay, the green spheres are nuclear charge. Chemists came up with a designation for atomic number to represent Z. I don't know why, I guess A was already taken. So capital Z represents atomic number, and effective means what actually is the electron experiencing for, the pull of the proton. So this would be a nuclear charge of 1. This is a nuclear charge or nuclear strength of 87, right? So as we go downward, our nucleus gets more and more powerful. And as we go across, it gets more and more powerful. Okay, to do what? Bennett, what keeps electrons in the atom? What do you know about electrons? Can you tell me 2 things? Yeah. They're ostracized? Oh, no. Quantized. Oh, now ostracized, that's like, okay, but you ostracized is like you're cast aside. You're like not included. Quantized, that's fixed distance or energy as far as the electron goes. You're right, you're on the same continent. All right, so electrons outside the nucleus, negative in charge. Quantized, but what keeps them? Excellent, excellent, excellent. Marcus, why are electrons attracted to the nucleus? So, couldn't they be repelled? Yes, you do. Yes, you do. Yes, you do. I know I had this big thing the other day about like, I know you know. I know we're like nervous, we don't, but I know you know. Ben. And Julian said it. I just want to make it more complete.
Was it because that positive energy around the nucleus helps the electrons to reach the ground state?
Positive energy? Is that like energy? Would we say energy? Energy, ability, to do work or cause change. So like positive, you know, go ahead, Jillian. Yes, 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 yes. There's a special fancy term for that, electrostatic attraction, positive and negative attracting. We know it just does. And like charges repel. So because the electron, now it's not a particle, we know that, it is negative and the nucleus is positive, they naturally attract. Again, the fanciest, you know, term is electrostatic attraction. That electrostatic attraction, positive and negative attracting, pretty much is what keeps our world together. Now, protons and electrons attracting, that can lead to, of course, atoms. Polar and non-polar regions of atoms can lead to solid state versus liquid state. We'll talk all about this. So positive and negatives attracting explains so much of why our world is how it is. All right, so what keeps the electron in the atom? The pull the nucleus has, but of course, electrons are pulling back. Not magnetic, but the same idea, right? A north and a south pole. Okay, so as we proceed down a group, the pull of the nucleus gets more and more and more and more. So think of a stronger and stronger and stronger magnet. The same this way, okay? Before we had kids, my husband and I went out west and we tried to visit in 5 weeks as many national parks as we possibly could. This is my youngin' days, not sure how I would do today, hiked down the Grand Canyon and then back up, which you wouldn't think like it's that taxing, but we were there in May and it's a mile of a vertical change. However, you do switchbacks to work down and switchbacks to go up. So I think in total, it's like 8 miles that you actually hike down and then 8 miles up. But we started out in winter clothes. And then when we got to the base, oh my gosh, we were just sweating and sweating because that much of an elevation change is a big change in weather conditions. We hiked out. Oh my, I thought they were gonna have to get a helicopter to take me. I was dizzy. I got elevation sickness because we just changed elevation too quickly. So it's my own fault, my own fault. So man, when we reached the rim of the Grand Canyon, I thought, oh my gosh, what a triumph. I can't believe I thought I was not gonna do it, but we just paced ourselves and we made it out. So this is like such a good memorabilia for me. So this means a lot. So has anyone ever been to the Grand Canyon? Grand Canyon's amazing because it's so big. There are other national parks, I think, that are, you know, more mesmerizing, but it's just so honking big. So I hiked, dragged myself, complained. No, I just was nearly passed out and barely made it out of the canyon. Yeah, but I did. I did. I'm so proud of myself. Okay, where am I going with this? Oh, so I love this magnet. But can I tell you, this magnet, it is about the weakest magnet you could ever have. I just put it here, but it actually doesn't hold up anything. So it is such a weak magnet that if I tried to hold up something, let's see, those have, well, it just wouldn't. So it can't even attract through a piece of paper. But these magnets, these much more powerful. In fact, as soon as I get kind of near the board, I can let go and they jump to it. So such a weak magnet, this pathetically can't even, you know, hold up a piece of paper, where this, I probably could hold up, I'd say, a piece of cardboard. So this is, now they're magnets, but that's what I'm talking about as far as the strength of nuclear pull at the top versus the bottom. And then at the far left versus the right. Okay, if we think of it as a magnet, we're getting more and more and more powerful. Or Cameron. So strong. Mrs. Gerhardt. So we could think about like strength, magnetic pole. All right. But it's not just about the nucleus. It's also about electron location. So we know the nucleus, we wouldn't show it as a dot, but we'll get the idea. Okay, I'm going to choose another color. And with this other color, I'm going to draw energy levels. Energy levels. And energy levels are not paths. But it's hard for me to draw a sphere. So we'll just use our imagination. Okay, Jackie, hydrogen. Hydrogen has how many energy levels holding its electrons? Yeah. I probably should have drawn that a little smaller, but we'll go with it. Okay. And then, Luke, what about lithium? How many energy levels? Yeah, right? 2s. That's its outermost electron. So I have 2. And then, of course, sodium, 3. Again, not paths, not paths. These are shells, right? They're kind of spheres where orbitals are found. Okay, we're just doing this for like visual sake. And then 4. And then 5. And then 6. And then 7. Woo! So for definite dramatic sake, so I can tell the size. Go ahead, Jillian. Oh, very sorry. I thought you shared because your contributions are so good. Sorry that I asked. We can see, can't we, that as we proceed down a group, and down, I mean, from the first period to the 6th period, our radius increases. So radius increases. I'm just going to use an arrow pointing up, down a group. So we would always judge bismuth to be larger than phosphorus. We would always judge osmium to be larger than iron, and tungsten to be larger than molybdenum. So that is just something that we can just know. Yes. I know. So can we pause and I'll come back to that in just a second. Would that be okay? Yeah, that's excellent thinking. But if we could pause and come back, and then I'll actually ask you to answer it. Okay, so the deal is, why do we get larger as we go down a group? Well, for crying out loud, we're adding additional layers of electrons. So as proceed down a group, additional energy levels, right? And you know that if I abbreviate, you may abbreviate. So EL, energy level, additional energy levels are added to hold the outermost electrons these outermost electrons are further from the nucleus which equals increased size of atom. Neon, could you choose an element for us? Any element. Neon, that's a great choice. All right. It is impossible to measure from edge to edge of an atom. We know that the edges are fuzzy because the electron is smeared out. There isn't a definite start and stop. but we can locate the nucleus because that is a large positive. So what we do is we bond one atom of an element to another atom of the same element. We pinpoint the nuclei, measure the distance between them, and divide it in half. And so officially it's atomic radius. We can just double it to be diameter, but we just reference it to be general size. Okay, so that's why it says atomic radius. It's one and the same with the size of the atom. Totally fine, totally fine. So can we envision that we're just adding layer upon layer upon layer upon layer? But then what's happening across the same period? So if we look at potassium over to krypton, potassium is in 4s. So 4 energy levels. After 4s with scandium, where do we put electrons? So this is the 4s. Then where do we go? SC. 3D, and then 3D1, 3D2, and so on and so on and so on. So 4th energy level, and then we go a little closer to the nucleus and keep adding electrons. And then when we're filled to 3D, where do we go then? Say again. That would be here. So I'm 1 period below. 4p. 3, 4, 3, 4. Same number of spheres. Okay. But we're working our way to be a Cameron strength of nucleus. Now I'm this wimpy. And then if I lifted some weights for a couple years, maybe I'd be there, still not anywhere the strength of Cameron. So here's me as a nucleus, and there's Cameron as a nucleus, but the electrons are the same energy level. With every move from potassium to krypton, our nucleus is getting stronger and stronger and stronger at pulling electrons. And the electrons are being added to the same energy level. So as we proceed, size decreases. So over here, we still have 4 spheres, 4 layers, but that strong nucleus can pull so much more strongly on those 4 layers. So as we proceed across the period from left to right, we actually get smaller. All right, so I will try to. I hope that's kind of. So we're getting smaller. Okay, so across the period, our nuclear strength is increasing as more protons added to the nucleus. But the electrons are added the same distance from the nucleus. Really the same energy level, right? So as a result, the stronger nucleus exerts a greater force of attraction on the electrons equaling a smaller size of the atom. Ben, does that make sense, sir? Does that make sense? Because if we don't mentally wrestle with it, we just always want to say, well, as atomic number increases, we have more protons, neutrons, electrons, we're just going to get bigger. So as we go down the group, we get bigger. And as we go across a period, we get bigger because there's more stuff there. But it's where is the stuff? I cannot think of a better, another kind of example that illustrates that. Where, you know, the nucleus is getting more and more and more powerful, but the electrons are added the same distance. So Jillian, to your question, which was so fantastic. Okay, as we proceed down a period, do we get larger or smaller? Yeah. And as we go to the right, larger or smaller. So we get bigger, but we get smaller. We get bigger, we get smaller. We get bigger, we get smaller. So what would you say about elements on a diagonal? Yeah, and you're right, somewhat even, because it depends on, oh my gosh, you know, have we just added an S and a P? Have we added S, P, and D? So there's some other things at play, but in general, the same. So I'll never give you elements on a diagonal to rank or compare. So that was excellent, excellent thinking. All right. $750 question of the day. What is the largest atom? What is our largest element? Ben?
Is it France?
Because?
Because the distance between each like energy level is the greatest, and it's the biggest, has the biggest nucleus.
Of any element? What do you mean biggest nucleus? No, you're really, really close, sir. So it has its electrons in the 7th energy level. And that's pretty much any of our ground state. That's as far away as you can get. But so does radium. So does seaborgium. So does, but you said the biggest? That's only 87. What happens, Ben, to size as we go from left to right?
It's decreasing, right?
Yeah. So it's actually because of its period, it has the lowest nuclear strength. It's the weakest magnet for those 7th layer electrons. Yeah. All right. Who's the strongest superhero? Is there a strongest? I don't know. If I wanted a superhero to take care of us, or rather you guys, because you're so precious, Superman? Wait, is Thor strong? I'm sure he'd be so insulted that I'm even posing the question.
I didn't have to watch much, but all I've really seen is his strength to be able to hold a hand.
I know, but yet he's like, you know, psychic. Oh, okay, we're going Superman. For crying out loud, he can make diamond in his own hands just by squeezing coal a little bit. So we're gonna go with, all right. So anyway, that Superman. So, you know, Would we say that's Superman? Yeah, because we want a lot of protons there. So I wouldn't want to say like Superman is fluorine's nucleus. But we know these are smaller than these. Oh, I don't know. I was trying to come up with a better example, and that was just a fail, a tremendous fail. Okay, could I ask Emma? So what would be larger? Phosphorus or aluminum? Yes, and that is just going to take us to just sit down and really work our brains to understand. So as we go to the right, we get smaller. We get smaller. Yeah? Yes. We're just talking about the size. So there's a lot of ways that we can measure strength. And so like strength of what, you know? So is it like we're talking about the force of attraction between the nucleus and the electrons, it gets stronger. Yes. But we could also say the force of the nucleus for the electrons, like in the lower energy levels, also gets stronger, but the distance trumps that. So yeah, the question is like, what do we mean by you know, stronger? But that was a very good point. How about this? I thought giving us this reference in color might help. So you have charts. We'll take a break in a moment. You have charts, of course, in your unit packet. And I really thought getting, and this is just like to reference. So it's trying to show us to scale what the size of our metals, non-metals. I find it really interesting how they chose to show metalloids. Okay, now the blue spheres are our metals. Okay, ignore the ions for now. And the yellow are our nonmetals. So if we look from potassium to krypton, oh my gosh, do we see how small we get? And then as we go downward, do we see how we increase? And so I hope that maybe, you know, to see that will help. Okay, Stacy, we'll ask 2 more questions and we'll get 5 minutes to brain break. Okay, Stacy, which is smaller? Which is smaller? We'll do calcium or barium. Why? As we proceed down a group, do we get larger or smaller? Yeah. So which is smaller, calcium or barium? Yeah. I'm not a fan of like childish, I think might be too elementary of things. I don't know. This kind of like, I don't know, is right on the line. So I've seen many teachers say when they talk about atomic size, and I guess so timely for yesterday, they show a snowman. I think our snowman will have a top hat and buttons. All right, whatever. Okay. That's supposed to represent atom size as we go down a group. We're adding bigger portions because those are additional layers of electrons. Well, that just not nice neighbor comes along and hits over your poor snowman. And that's supposed to be across a period. I don't know. Is that a little, yeah, I don't know. But we have to understand the why of it. But that can help maybe. Okay, so Stacey, another one coming to you. So which is smaller? Chlorine or bromine? Yes, 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 because it's higher up the group. All right, let's see. Sophia, which is larger? Which is larger, iron or titanium? Excellent. All right. So if you have any concerns, questions, let's take a brain break. So could I get you back at 1:04 in your seats, please? If you're going further than the restroom or water fountain, let me know. I'll write you a pass, of course.